All right, so if we want to calculate acceleration, right, then we're going to use this formula here. Okay, acceleration equals VF minus VI over t, right? We can't use y equals mx plus b here because we have too many different sections. Okay, so what I need to do then is find VF, okay, for between A and B. So VF would be 20 meters per second. VI would be 0, and that took 2 seconds. All right, so that would mean that my acceleration is positive 10 meters per second squared. Everybody all right with that one? Okay, not too tough there. Is the positive important?
Yes.
Yes. Okay, and then the total displacement between A and E. How many people have done the total displacement? Okay. So if I want to find the total displacement between A and E, that means I've got to find average velocity times time for each section of the graph. All right, so for this first 2-second section, that's going to look like this. Okay, it's going to be that triangle. And then I'm going to say, there's a number of ways you could do this, but I'm going to say a way to do this would be to go all the way across and have that rectangle, and then this triangle and that rectangle. Okay, you may have done this rectangle, that's fine. Okay, there's lots of different ways to get the total area underneath this line. All right, it should all come out to the same answer regardless of which way you decided to do it. All right, so for me, the first shape here has a base of 2 and a height of 20, so 2 times 20 is 40, divided by 2 is 20. All right, so that's going to be positive 20 meters. Then I've got this rectangle that has a base of 1, 2, 3, 4, 5, 6, and a height of 20. So that'll be 120 meters in there. Okay, I've got this little triangle that has a base of 1 and a height of 20. 20 times 1 over 2 is 10 meters. And then I've got this rectangle here that has a base of 3 and a height of 20. So that should be 60 meters in there. All right, so if I add those up, I got 140, 150, 210 meters. Everybody all right with that? And like I said, you would have got that number even if you had chosen different shapes. If you chose like one big tall rectangle and this little rectangle, would still come out the same answer. Okay. All right, I will give you guys a few more minutes and then we'll look at C, D, and E. Keeping in mind that if you're going to get average velocity between A and F, you need the total displacement for that. So you've got a couple more shapes you're going to have to put on that graph. All right, so if we want to find the acceleration between F and G, between F and G, how many marks would that be out of on a test? 1, because what's the answer?
0.
Right. Okay, it's strictly recognition. The velocity of the object is not changing between F and G. The acceleration is 0. Okay. All right. The average velocity between A and F. Well, if I'm going to get average velocity, I need the total displacement and the total time. All right. That means I've got a couple more shapes I've got to add to my graph here. I've got this little rectangle that has a base of 2 and a height of 20. Okay, so it'll be 40. And then I've got this one here, so now we're up to 250, right? Plus whatever this triangle is, okay? And it has a base of 2 and a height of 20, so it's going to be 20. So we're looking at 270 meters, okay, as our total displacement. Okay, divided by our total time, so the time is from 0 to 10 seconds. Okay, so we should get positive 27 meters per second as our average velocity between A and F. Everybody all right with that? Okay. All right, and then the total distance traveled. Well, now we can finish off the graph and get all the shapes, okay, that we now have to have. All right, so I'm going to just finish off with that rectangle there that's exactly the same size, so I can save myself some calculating and just know that it's, okay, 40 meters. That's going to be now 310, plus the little triangle on top of it that has a base of 1 and a height of 10. Okay, so 10 times 1, this will be another 5, so we're looking at 315 meters as our total displacement. Everybody all right with that?
It says total distance traveled.
Total distance traveled, 350. Yeah, I don't have to put a positive on that because it's scalar, it's asking for distance. Right? Everybody okay with that? Would I give you one that has that many little shapes and calculations on a test? No, you'd be looking at probably a graph that would have two, like a triangle and a rectangle, or maybe three. Okay, but no more than that. I just need to know you know how to do it, not how many of them you can do. Right, but this is just good practice. All right, last week, we're going to kind of go back between velocity versus time graphs and acceleration stuff here today, guys. Okay, last week we were working on acceleration problems, okay, using that A equals VF minus VI over T formula, right? So I want you guys to see how you do with this one. You're looking for the final velocity of the plane. Right, so I'll give you a couple minutes, okay? Write down your givens, choose your formula, manipulate, solve. Okay, so we got a plane lands on a runway at a velocity of 200 meters per second. So what was that they just gave me? Initial velocity, right? Okay, over a 15-second interval, what did they just give me there? Time. Okay, it slows at 6.5 meters per second squared. What did they give me there? What do I need to remember about it?
Negative.
That's right, that's negative. Okay, and that's like really about the only trick they can play on you in an acceleration question is to say slows down instead of the acceleration is negative 6.5. Okay. All right, and so we're looking for the final velocity of the plane. So we've got A equals VF minus VI over T, and we're looking for VF. So according to the rules of algebra, I move what's not attached, T, first, multiplying, which is doing the opposite. Right, so T comes over here, and then I would add VI to both sides. And now I'm solving for VF. So I would have 200 plus 15 times negative 6.5 equals VF. Right, so when I punch that into my calculator, okay, so I would have 200 plus 15 times negative 6.5, me 102.5 meters per second, and that would be positive. 102.5. Everybody all right with that one? Okay, how are we feeling about the acceleration problems and using the formula? It's kind of what I thought. Okay, this one's a little trickier. It gives you almost nothing, or at least it seems that way. Okay, it actually gives you quite a bit, but you have to get it from the context of the question. So this is about as tricky as they get, not mathematically, but contextually. Okay, this is like reading comp. There's no hidden meaning, but like you still have to get the hidden stuff. Okay, there's no hidden meaning, but there's hidden stuff. Okay, what are the tricks to this one? What's that? Gravity is your acceleration. Okay, so that's the first trick. We have to recognize that since it's falling, the acceleration due to gravity is negative 9.81 meters per second squared, or 9.81 meters per second squared down. Okay, I don't really have to make it negative because it never goes which way? Up. Yeah, so it doesn't really matter. Okay, what's the other trick? Right, VI is 0. If something just falls, then its initial velocity is 0. It's essentially starting from rest. If it's thrown or shot or something like that, then it would have some VI that's not 0. But in this case, because it falls or is dropped or something like that, VI equals 0 meters per second. So those are the two tricks in that one. Okay, we're looking for how long it will fall for, and it reaches a final velocity of 42 meters per second. That's also down. Since there's no up, I'm just going to make them both positive and not worry about it. Okay, so A equals VF minus VI over T. Okay, we're solving for T this time, so we're going to multiply both sides by T, divide both sides by A, and and plug in our numbers. So that'll be 42 minus 0 divided by 9.81 meters per second squared. All right, so we're looking at 4.28 seconds. For our total time to fall that far. Everybody all right with that? All right, let's look at another graphing one here. Okay, see if you can do that one. So we got a velocity versus time graph. Okay, we're looking for acceleration, total displacement, average speed, okay, and a second acceleration calculation as well. All right, give you a couple minutes on that one. Some reading of the graph. What's going on in this first section of the graph? It's accelerating forwards. Okay, what's it doing here? Moving at a constant velocity of 1 meter per second forwards. Okay, that would be like the 5 out of 5 answer. Okay, just saying moving or constant speed would not. Okay, because we can get that much information from it. All right, what's it doing in this part here? Accelerating forwards. Okay, but no. Okay, but I still hear people saying accelerating at a constant velocity. You cannot do both. You are either traveling at a constant velocity or accelerating. You can say accelerating uniformly, that would be true. That would be accelerating at a constant rate. But you cannot say accelerating at a constant velocity because those two things are opposite. Okay, so just be watchful of that because I see people write that on unit exams. And then I'm like, well, which is it? It can't be both, so it's wrong. Okay, I don't want that to happen to you, so don't say that. All right, what's going on here? Traveling at a constant velocity of positive 3 meters per second. What's going on in the last part? Accelerating negatively. Okay, you could even say coming to a stop. Yeah, because it does eventually reach a final velocity of 0. All right, so for part A, it wants to know the acceleration between 7 and 9 seconds. So that means starting right here and ending right here. So acceleration is Vf minus Vi over t. So that's going to be 0 minus 3 divided by 2 seconds. So we're going to get negative 1.5 meters per second squared. All right, everybody okay with that one? All right, total displacement between 0 and 7 seconds. Okay, so I'm going to have this part here where it's accelerating. And then I'll probably just do this straight over to 7 seconds. Get one big rectangle there, get a triangle here, and a rectangle there. And I'm going to have to do this triangle eventually, but not right now. Okay, so if I'm calculating all of these, okay, so I'm going to have a base of 1, a height of 1, so that's going to be 0.5. This rectangle here goes 1, 2, 3, 4, 5, 6. Right? This triangle here has a base of 2 and a height of 2, so it's 2. Okay? And then this rectangle here has a base of 1, 2, 3 and a height of 2, so 6. All right, so we're looking at 12, 14 and a half. Positive 14 and a half meters. Everybody all right with that? And then if we're going to find the average speed over the whole trip, average speed is total distance divided by total time. Okay? We already know the total time is 9 seconds. Okay? But we don't know the total distance because we still have to find this triangle here, which has a height of 3 and a base of 2. Divided by 2 is 3 meters. Okay? So now we'll add that to our 14 and a half for 17 and a half. Divided by 9 should be 1.94 meters per second. Questions on that? And then the acceleration between 2 seconds and 4 seconds. So acceleration is Vf, 3, minus Vi, 1, and that is for 2 seconds. So positive 1 meter per second squared. Okay. Everybody all right with how that one worked? How are we feeling about the velocity versus time graphs? Okay. A little better than last week at least? Okay, switch gears. See what you remember. This is a position versus time graph. Because on a test, you're going to get both. You got to be able to switch gears quickly between velocity versus time and position versus time graphs. Okay, so we're looking for average speed over the whole trip, average velocity between 300 and 500 seconds, and because this is really hard to read, this is 250, okay, this is 500, this is 750, 100, 200, 300, 400, 500. Okay. All right, let's do the same thing and analyze this graph first. Okay, what's going on in part A? Okay, it's positively increasing its position, not its speed. Its speed is constant. Okay, this is a position versus time graph. So what we are seeing here is that the position of this object is changing by the same amount every time interval. It isn't going faster, or it would be a curve. Okay, it's a slope because its position is changing at a constant rate. And remember, velocity is change in position over time. So if it's showing a diagonal line, it's moving at a constant velocity because of that. Okay, so in part A, it's moving at a constant velocity. What's it doing in part B? Moving at a constant velocity. Where is it moving faster, A or B? Because it's right. Okay, what's it doing in part C? Nothing. Right, it's sitting still. Okay, and what's it doing in part D? Moving at a constant velocity backwards, right? Not accelerating, okay? It's not a curve, okay? It's moving at a constant velocity because its position is changing at a constant rate. Acceleration looks like this, okay? Its position is increasing at an exponential rate, okay? That means it's moving faster and, as a result, farther every second, okay? Here, it's moving farther every second, but not faster. Okay, every second it goes the same amount. Sorry, I said that wrong. It goes the same amount of distance every second. Okay, but each second obviously is going to be further by the same amount than it was the second before.
Would we ever have to do like calculations for an acceleration on position versus time graph?
No. Okay, you just have to be able to recognize. You might have to recognize this is speeding up, where this is slowing down. Okay, what would this one be? It's slowing down backwards. Yeah. Okay, and this would be. I gotta draw it the right way. That would be speeding up backwards. Yeah. Okay. So now we'll get to the actual calculations that this question asks us to do. So average speed over the whole trip. All right, if I want average speed, I need total distance and total time. So my total distance means figure out how far it goes in each section of the graph and add them together. Okay, so in this first part of the graph, we go from a position of 0 to a position of 500. So that's 500 meters. Then we go from 500 to 750. So that's another 250 meters. And then we go another 750 meters. So our total distance here is 1,500 meters. Everybody okay with that? Okay, and the total time is 500 seconds. So 1,500 divided by 500 is 3 meters per second. That's scalar because they wanted us to calculate the average speed. Okay? Now, velocity between 300 and 500 seconds. All right, average velocity is change in position, or displacement, divided by time. So my final position is 0 meters. My initial position is 750 meters, and the time is 200 seconds. Okay, so I'm going to have negative 750 divided by 200, which should be negative 3.75 meters per second. Okay, is the negative important on that one?
Yes.
Absolutely. Okay, total displacement over the entire trip, 0. Initial position, 0. Final position, 0. Didn't go anywhere because we came back to where we started. All right, distance traveled in the first 200 seconds. 500 plus 250, 750 meters. Again, that one doesn't need a direction on it because that's for distance, which is scalar. Okay, that was on an exam years ago. Okay, that exact question.
So for the one where you put the negative, if you just put backwards, is it the same?
Backwards would be fine. Yeah. Okay, any other questions on that one? That was the last one for that. Okay, a couple more of these. Okay, so this is the toughest manipulation of your acceleration formula, solving for VI. All right, so I'm going to give you guys a little bit of time to get that one done. Okay, solving for initial velocity on that. So for this one, okay, it tells us the race car reaches a velocity of 80 meters per second. Is that initial or final? Final, okay? Because it says after accelerating. So that's our final, 80 meters per second. Okay, the other dead giveaway that was the final was it later asks us to calculate the initial. Okay, always a good sign. And it says after accelerating at 4.5 meters per second squared for 12 seconds. Okay, looking for the initial velocity there. So A equals VF minus VI over T, okay, and we're solving for VI. So I'm going to first multiply both sides by T, then I'm going to add VI to both sides so that it comes out positive, and then I'm going to subtract T times A over to the other side. So we'll have VF minus T times A equals VI, so that'll be 80 minus 12 times 4.5. Alright, so we're getting an initial velocity of 26 meters per second, and that would be positive. Alright. Everybody okay with that? Alright, I'm going to give you about a 5-minute break here, so we'll say 9:49. Okay, we'll resume. Obviously, you can't leave the room anymore. Yeah? Alright, so we've got about 10 minutes left or so. What I would like you guys working on is the stuff from your physics worksheet package, which is on Google Classroom. Okay, and I'm going to want you to work on just a few specific ones here. I am going to want you guys to do number 2, number 5, number 6, and number 7. Okay, so 2, 5, 6, and 7 are the ones I want you to work on, kind of finish things out here. And if there's any problems with those, we'll go over them together.